Hi, my name is Szymon and I'm a PhD student at Wrocław University of Science and Technology and the Faculty of Mechanical Engineering. Today, I'm going to present you our research that concerns mechanical performance assessment of composite bars. So the main idea of the research is to determine the mechanical properties and quality of the manufactured composite bars. And it is a part of the application project that concerns a new generation of the hybrid composite rods for a concrete and soil reinforcement. So we want to deliver a high performance bar that provides better mechanical performance that currently available on the market, and it will be for the concrete and soil reinforcement. So as an introduction, I would like to point out that we manufacture three kinds of bars, such as glass fiber reinforced polymer, basalt fiber reinforced polymer, and the hybrid one. So the core is made of basalt fiber with the glass fiber, and it is unidirectional, of course, material with the epoxy resin. So we use the pultrusion system, as you can see in figure 1. That's our main manufacturing system. So with these bars, we perform 3 static mechanical tests, such as tensile test to determine the Young modulus and tensile strength. To be honest, this test is quite challenging because of the anchoring system as well as the sample length. Then flexural test. So we determine the tangent modulus of elasticity, so in bending, right? Then short beam, we examine the apparent shear strength. And I also put here the transverse shear strength. So that's also the alternative for this short beam test. So moving on, let me start with the tensile test. We used 9 samples, 8 of them with 6 millimeters of diameter, and 1 was with 10 millimeters. And as for the anchoring system, we used epoxy resin with quartz sand, and it was the steel tube was filled with this mixture, and also there was a bar that prevent the slipping of the bar, and we could grip the steel tube in the testing machine. Because of some limitations caused by our universal testing machine, we needed to increase the adhesive strength inside the anchoring system, because we could have not provide the proper length of the anchoring system that is mentioned in the standard. So we used a primer with quartz with a different grain diameters, like you see here. It's up to 103 micrometers. Then just the primer, sandblasting, and finally the quartz sand, but with greater diameter up to 0.6 micrometers. So we used the displacement control mode with 2 millimeters per minute. And in the figure F3, you can see the experimental setup. We use DIC, so digital image correlation, to measure the strain during the test. And here in the table, you can see the length of this part, and LA is the length of the anchoring system of the one anchor. So then flexural test. This test is quite interesting because we need to prepare a special samples that are cut along the bar axis, or we can just manufacture such profile or shape using the pultrusion. And the reason is that we need to decrease the compression area in the bar. As you can see, there is a strain distribution for the compression side, and this one is for the tensile one. And we use the glass fiber reinforced polymer with the 10 millimeters of diameter. We cut it through the bar's axis, and we use the displacement control mode with 3 millimeters per minute. Okay, then short beam test. So here we use more samples. So GFRP with 10 and 6 millimeter of diameter, then basalt fiber reinforced polymer, and the hybrid one. And the hybrid one is with 8 millimeters of diameter. So the displacement control mode with 1.3 millimeters per minute, and we calculate the apparent shear strength as it is presented here. That's the formula for this, where P is the breaking load and D is the diameter. Here we can see the test stand. And now let me turn into the results. First of all, the modulus of elasticity. So here we can see in the figure 8, we can see the results for the basalt fiber reinforced polymer. And here in figure 9 for the glass fiber reinforced polymer. As you can see in the table, it's possible to, so we put here the value of the Young modulus, and also from the 9 samples, 3 of them did not withstand the applied load. It means that the adhesive strength was not enough and we had a pull out. So we could not determine the Young modulus, and mainly the primer with quartz sand up to 0.3 millimeters was not a sufficient way to prepare the surface for adhesive strength increasing. Then the results for the modulus of elasticity in bending, and yeah, in figure 10 you see the force deflection relation for the flexural test. And here it's possible to see the equation for the modulus of elasticity. So we use it, and it's according to the ASTM standard. And we see that the average results for the flexural module, it's approximately 80 gigapascals. Moving on, the results for apparent shear strength. So we see four graphs with the results for a different specimen batch. So here we have for the basalt fiber, then for the glass fiber, and here it's for the C. So it's also a glass fiber, but with the greater diameter. So it's 10 millimeters of diameter, and H is a hybrid one. And as we can see, the hybrid one exhibits the greatest apparent shear strength, 58 megapascals. And this H bar is a combination of glass and basalt. And we see basalt has about 57 and glass 53. So the lowest one is for the bar with 10 millimeters of diameter, and for the glass it's 49. Okay, so post-failure analysis. We noticed that during the short beam test, the major failure was the interlaminar debonding and also the fiber kinking. In case of the flexural test, the major failure mode was the delamination and the fiber breakage in the outer surface, the area or the surface where was which was tension. Here we see the strain distribution along the bar, and it's the screenshot from the DIC software. And figure 15 showed the damage sample after a tensile test, and it's of course, and it was in this case matrix cracking and fiber breakage. Okay, so the comparison, I put here the results from our test, mechanical test, as well as the results from the literature. And as we can see, the main advantages of our bars is very high tensile strength. It's about 1,400 megapascals, where in the literature I've noticed only about 1,200 megapascal. So that's quite a lot for the bars. In case of the Young modulus, so we have a 44 gigapascals for the GFRP and 50 for the BFRP. There are the greatest. The Young modulus in the literature I've noticed greater, but we need to be aware that the fiber volume is the crucial factor here that decide about the stiffness of the structure or material. And we had in our case it's only 62%, and in case of this data, so it's a 75%. So that's why the Young modulus is greater. And as a conclusion, so the most challenging experiment is, of course, the tensile test due to the anchoring system that needs to be provided. So we use a various surface preparation that prevent pull-out from the anchoring. And the outcomes show that the tensile strength for both materials are approximately 1,400 megapascals, and Young modulus is about 50 gigapascals for basalt and 44 for glass fiber reinforced polymer. So Flexural Test allowed us to determine the modulus of elasticity in bending. This experiment requires a special prepared sample bars to decrease influence of the compression stress. And the glass fiber reinforced polymer exhibit flexural modulus around 80 gigapascals. The determination of apparent shear strength required conducting short beam tests, and this experiment shows that the greatest strength exhibit hybrid bars, so the basalt and glass fiber. And this particular configuration is a combination of basalt and glass fiber in epoxy resin. Finally, several failure mechanisms were determined during the mentioned experiment. So interlaminar debonding and delamination failure appeared in Flexural Test. On the other hand, fiber breakage and matrix cracking were major failures appeared in Tensile Test. So thank you for your attention.